Hello everyone, today we're talking about section 3, using functions involving the number e. And if you remember from first semester, we did those math in nature projects. We did talk about a little bit the number e and what that comes from. So for today, students will be able to use functions involving the natural base e to model the visibility of water. There's lots of things that an e can model, but that's one of the things that we'll look at. So first of all, we need to know what is the number e. So the natural base e is Euler's number, which is equivalent to 1 plus 1 over n to the nth power, which is the value of e as n increases to infinity. So you take that value and you keep plugging in values all the way to infinity, and it becomes e, which is approximately 2.718281828, and it goes on forever, okay? So, now keep in mind, we're going to be simplifying with the number e, but I want you to remember properties of exponents. And remember that when you have some base to an exponent times the same base to an exponent, we keep the base, and multiplying exponents is really adding them. So we add them up top. So when we want to do that to simplifying with just the number e, this could be just like any other number. It could be 2, it could be 5, it doesn't matter. So because these are the same base, we're going to keep the base, and multiplying exponents is really going to add them. So this becomes e to the 7th. If we were to simplify here, just like in our previous lessons about exponential properties, we can separate this, and we can do 12 over 3 times e to the 4 over e to the 3. So let's simplify this first. So I know 12 divided by 3 can simplify to 4. And e to the 4 over e to the 3, remember in our properties, when you have some number to the m exponent over the same number divided by another exponent, we keep the base and subtract the top minus the bottom exponents. So we're going to keep this and say keep the e and take the top minus the bottom exponent. So we're left with 4 times e to the 1, which is just 4e. Okay, and then lastly, for this one, because they're being multiplied here, we can take this exponent and distribute. We could also rewrite it twice. So this becomes 5 squared times e to the negative 3x squared, because we distributed the 2 to both parts. So now I know 5 squared is really 25. And when I raise a power to a power, we multiply them. So remember, when you've got a to a power, you raise it to another power, this becomes a to the m times n. So we go e to the negative 3x times 2. This is 25e to the negative 6x. Okay, now keep in mind, we don't normally like to have negative exponents. So this right here, we're going to make a positive exponent. We're going to leave 25 here, and this e becomes 1 over, because remember that exponent, whenever we have a negative, becomes 1 over, e to the 6x goes under, so we're left with 25 over e to the 6x. And that's our answer. Okay, so what if we wanted to use our calculator to evaluate something? All you're going to do in your calculator is you're going to find the button, and it usually looks like a button that looks like this, e to that, which means it's telling you e, and it's going to raise it to whatever number you push. So in your calculator, you're going to find this key, and then you're going to just hit the number 4 and then your equals or enter button. So we get e to the 4 in your calculator, hit enter, and we get 54.59815003. So we're going to round it to 5981. Okay, for this one here, we're going to use that e to the key. Sometimes the key looks like this, e to the x, and then we're going to hit the negative button, and then we're going to type the numbers 0.09. Hit your equals key or your enter key, and we get 0.9139. Okay, so you just need to be comfortable with putting that into your calculator. If you need help on that, come see me. So now we're talking about what the graphs look like. So a function and the form of a times e to the rx, remember your base is a number e, is called a natural base. This is not unlike the same shape as we've been talking about a times b to the x, where b was just a number. E is also just a number, it's just a specific number. So if a is greater than 0, we call that positive. And r is greater than 0, we also call that positive. The function is exponential growth. If a is greater than 0, which again is positive, and if r is less than 0, we call that negative. It's an exponential decay function, okay? So we can see here, this is our exponential growth, and this is our exponential decay where we had a negative exponent here and a positive exponent here. So if I want to graph this, how would I graph y equals e times x to the 0.25x? Well, here's the thing. Just like before, we're going to use the same 3 steps. The first thing we're going to do is we're going to make our chart. So here we go. We're going to plug in the same values we've been using, -1, 0, 1, and 2. And you're going to use your calculator. And I'm going to plug this in, and we're going to say our value for y is 3 times e to the 0.25 to the times -1. Here's 3e to the 0.25 times 0. 3e to the 0.25 times 1. 3e to the 0.25 times 2. So now we're just going to evaluate each of those numbers in your calculator. We know this will simplify 3 times e to the -0.25. So in your calculator, you're going to hit the number 3, hit your e button. We're going to go negative button, 0.25, and we get, oops, I don't have it. We get approximately 2.4. I'm going to round it, okay? If I plug this in my calculator for the next one, we get 3 times e to the 0.25 to the 0 is still 0. E to the 0, we know is just 1. So this is 3 times 1 is 3. And that's a really important important piece of the information that it's going to hit at that point 0, 3. 3 times e to the 0.25 times 1 is just 0.25, and we get 3.85. And actually, that's enough points. We don't have to do the fourth one. You can if you want to, though. So as we're graphing, I'm going to take out my graphing paper, and I'm going to draw my graph. Here's my x-axis, here's my y-axis. So we're going to graph the point -1, 2.4. So we could go -1 in the x-axis, and then we're going to go up 2.4. That's about right here. So here's 1, 2, there's 0.4. And then we're going to go 0, 3. So at x is 0, y is 3. and that comes from here and here. Then our last one is 1 comma 3.85. So we're going to go over 1 up 3.85, and we're going to show them what that looks like. Okay, and it looks like this. All right, so there's our graph. Actually, it comes down a little bit more. I'm going to make it sure that it goes. There we go. Looks like that. Okay, so what happens, remember when we were talking about compounded interest? What if it's continuously compounded, meaning not yearly, not monthly, not weekly, not daily even. It's compounded continuously, meaning round the clock. We're going to use this formula. So when you see that word compounded continuously, we use this formula. A equals P times E to the RT. And P stands for that initial or starting amount. Some call it the principal amount. E is the number we've been talking about. That's the number E, that 2.71 number. R stands for the percent rate in decimals. And then T is for time. And this one, I believe, is in years. So looking at this, we can use this to model growth of many, many things. All right, and we're going to use this in class, and I'll see you next time.